Algebra 2 honors, notes for 4.8, we're analyzing graphs of polynomial functions. So today your polynomial functions will be given to you for graphing in factored form already. You don't have to do all the factorization. When you get, by the way, when you get to your homework, make sure you read through this. On 32 and 33 include intervals where they're increasing, decreasing. 41 to 43, you have to have algebraic work as I'm showing in the notes to support whether the functions are even odds. So anyway, going back to, you're going to get polynomials that you graph that are already in factored form. And we are going to use the x-intercepts to graph them. We're also going to be looking at the location principle. And we're going to identify turning points, local max and mins, and identify even and odd functions. Those are the different things that we're going to be doing. But when you get this polynomial in factored form, here are the steps. Identify and plot the x-intercepts, and the x-intercepts are when y is 0. You need to just, when you hear x-intercepts, y equals 0 should just pop into your head. Second, find and plot the x-intercepts, or excuse me, second, find and plot the y-intercepts, and that is when x is 0. Third, determine end behavior, cubic, I'm a little teapot, even, it's touchdown, or you have reflections of those. 4, evaluate the function for a few points between and or beyond the x-intercepts. Show a table of values. I'll model that as we go through. Draw the graph so it passes through all those things you just found. So when we go to graph the following, the first thing that we're going to do is identify the x-intercepts. And that is when y is 0. So set the function equal to 0, and it's already in factored form. So it should be easy to identify those zeros. It's already in factored form. And something to note is that at -3, you expect a bounce in the graph because it's to an even power. And when it's to an even repeated root, it goes to touch the x-axis, it turns around and goes back in the same direction. It doesn't pass through. Next, we need to find the y-intercept. And the y-intercept is when x is 0. You don't need to expand this, just put 0 in for x in the form that you have it. And work it out, and you get a -9. And then go to plot those. We've got an x-intercept of 2, we have an x-intercept of -3, and we have a y-intercept at -9. For end behavior, you need to know the leading term. And you don't need to expand it all to figure it out, I hope. For the leading term, you're going to take 1/2 times x to the first, because this quantity is just to the first, and times x to the second, since that's squared. So the leading term is going to be the 1/2 x to the first, but then an x squared, because that binomial would be squared. That's going to be the result if you expand it to get your leading term. And since it's cubic and positive, I'm a little teapot, it looks, we expect something like this. And so my end behavior is as x goes to -infinity, y goes to -infinity. As x goes to +infinity, y goes to +infinity. And the next piece is to evaluate this function for some x-intercepts between, or not x-intercepts, but some x values in between the x-intercepts and beyond. And so what I'm talking about is here at -4, that's beyond the leftmost intercept. So we should have that in our chart. And then at -2 and -1, those are x values in between the x-intercepts. At 0, we already know that it's at -9, so we don't need that again. We don't know where it's at 1, so there's another x value we should use. And then beyond the furthest right intercept at 3. And if we need to go further to the left of -4 or to the right of 3, you can add those in. And now you plug them in and you evaluate. And so it means that you're going to put f of -4 in and just put it into that factored form. And at -4, you get 3. So at -4, you're at -3. And so on and so forth. I'm not going to sit here right now and evaluate all of those. You need to do that, but we don't need to take time in class. According to the last test, some of you need to actually work on evaluating polynomials. You didn't nail it when you put them in to the function. So anyway, at -2, I'm just going to let you know what the value is. At -2, it's -2. And at -1, it's -6. At 1, it's -8. And at 3, it is +18. So at -2, it's -2. At -1, it's -8. We already know at 0, it's -9. At +1, oops, I apologize. At -1, it's -6. I went down to -8. At +1, it's -8. And at 3, it's at 18. That means as it passes through, it's going to be off the chart before it hits the vertical line x equals 3. And so don't forget, as you go to graph this, the bounce at -3. So it's going to be coming, remember this is the end behavior. So it's going to be coming from below. Come and do a turn at -3. It's got the bounce because that's an even repeated root. And we won't all look exactly the same, but it should be a smooth, continuous curve and should have arrows on it. So those are the steps to getting it graphed. And this is when it's in factored form. So repeating these steps in the next example, the first thing is the x-intercept, which is when y is 0. And since it's already in factored form, that's nice and easy. It's going to be 1, 4, and -2. And at -2, I expect a bounce because of the repeated factor an even number of times. So we have 1 at 1, 1 at 4, and 1 at -2. The y-intercept is when x is 0. So just put it into that factored form and evaluate. And we have a -32. So to make that fit, this is going to down by 10. I'm going to go by 4s. So -4, -8, -12, -16, -20, -24, -28, and there is my -32. So 4, 8, I'll just mark 12 there and we can keep on going as needed. So I'm going to go 4 on that scale. And then we need end behavior. So we need the leading term. And it's going to be the negative 2 times x to the first, since that's just a factor once, times another x to the first, but then times x squared because that quantity squared. My leading term is going to be a negative 2 x squared, which is a negative 2x to the fourth. So it's a reflected touchdown, and so I'm expecting, it could look something like this. Both ends down. So my end behavior, whether x is going to positive or negative infinity, y is going to negative infinity. The next step is to evaluate for x values between the x-intercepts and a couple or so beyond. And so I have at negative 3 would be an x value beyond the last x-intercept to the left. So I would use negative 3. We already know it's 0 at negative 2. I would use negative 1. I already know at 0 that it is negative 32. I already know at 1 it's 0. So then at 2, 3, and 5. At 2, 3, and 5. So that gets all the x values in between the first and last x-intercept, and then one x value beyond each. And I'm not going to take time to plug those in and evaluate them. You need to be able to do that. And so I'm just going to give you what they are. They're negative 56. At negative 1 is a negative 20. At 2, it's 64. At 3, it's 100. At 5, it's a negative 392. So, by the time, at negative 3, it is way off the chart. So, remember that left end is coming from negative infinity, so it's way off the chart. It's at negative 56. So show that it's not going to hit the vertical line x equals negative 3. It's going to be off the chart before it hits it. And then remember at negative 2 you have a bounce. And from there you're going to bounce, and at negative 1 you're at negative 20. So 4, 8, 12, 16, 20 is right there. So you're going to bounce, go through 32, start coming back up, and you're going to cross because at 1 it's just to the first power, so it will cross. And at 2 you're at 64, so we're going to just make it up. That's at 64. And then at 3, we're going to say that's 3 100, not to scale. And it's going to come around, and it's going to go super steep because it's going to cross through at 4, and then it's at negative 392 before it ever gets to 5. So that goes through the points I have. It has the bounce where it should have. It's got both arrows showing it's going down. It's got the correct end behavior. And that's what we're looking for graphing. All right, the next thing that we're going to talk about is the location principle. And for that, I'm just going to kind of introduce it, a little differently, graphically. Say at 2 you are at negative 4, and you're graphing a polynomial. And at 3, you're up at 5. Polynomials are continuous, smooth functions. So that means you're going to, be graphing your polynomial However, it's graphing, and you can't pick up your pencil, you got to connect the dots. The location principle says here at this integer, or it doesn't have to be an integer, but an x value, it's negative, and then at an x value a little greater than that, it's positive. You are guaranteed an x-intercept between 2 and 3. If the polynomial changes in sign from negative to positive, you must have crossed the x-axis. So you have a 0 between 2 and 3. Whatever that says. You have a 0 between 2 and 3. You're guaranteed because, and that's something you do in AP Calc. You say it's important you say that the function is continuous. All polynomials are continuous. And since the function changes from negative to positive, between these two x values, there must be a 0. You're guaranteed it. And so say, you got 4. At 5, it's back at 5. And at 6, it's at negative 2. So it's a polynomial, it's continuous. Because at 5, it's a positive 5, and at 6, it's a negative 2. There's also a 0 between 5 and 6. It's a smooth, continuous function. You can't pick up your pencil. You have to cross the x-axis if the y values change in sign. That is the location principle, and that's what they're talking about on the back side. The location principle, how they talk about it more formally, you have a polynomial function. A and B are real numbers, and this is just a fancy way of saying at 8, the function's negative. And at B, the function is positive. Well, since it's a continuous function, f has to have one real 0 between A and B. So in this example, given below, between what pairs of consecutive integers does f of x have at least one 0? And we're assuming it's a polynomial. And so you're looking at the y values. The y value changes sign from positive to negative, but it is the x values for which between there will be an x-intercept. So you have zeros between negative 1 and 0. That's one pair. If you keep on going down, at 1, the function's below the x-axis. At 2, it's above. The output changes from negative to positive. So there's got to be a 0 between 1 and 2. So you're looking at the y values to see if there's a change in sign, but it's between the x values that their 0 is. And then the next change in sign in y is when x is 3 and when x is 4. At 3, you're above the x-axis. At 4, you're below. So there must be a 0 between 3 and 4. And so that one, it might seem very obvious to you, but you do need to attach that to the term location principle. And so that's something that you want to review to have the vocabulary fresh in your mind. All right, and then we have turning points. Another important characteristic of the graphs is that they have turning points. Turning points are here and here on this graph. It's where the functions change from increasing to decreasing or vice versa. Those are turning points. And if the function changes from increasing to decreasing, you have a local maximum at that point, and it's the y-coordinate that is the local maximum. If the function is decreasing and changes to increasing, you get a local minimum. It's the y value that's the minimum. And again, as we do increasing, decreasing, you're always driving from left to right. So this function increases, decreases, and then increases. And to identify the increasing, decreasing, you use the x values of the local max and mins. And also new this year is you include them. So instead of open, you include them. The textbook will have them probably open. You need to have them included. So the turning points help us determine intervals for which the function is increasing and decreasing. Then over here, a core concept. The graph of every polynomial function of degree n has at most n minus 1 turning points. If you have a polynomial of degree 6, the most number of turning points you can have is 5, one less than the degree. On the other hand, if you have a polynomial function of degree n and it has n distinct real roots, so say that you have a polynomial of degree 5 and it actually has 5 zeros, distinct, not repeated, then its graph has exactly, you're guaranteed 4. So if you don't know if it has exactly n zeros that are distinct, you can have up to n minus 1. You don't have to have that many. But if you know it's of degree n and it has n distinct, then it does have n minus 1 turning points. So when you look at this, it has 2 turning points. It's got to be at least of degree 3. Has to be at least of degree 3. All right, so given a graph in example 3, approximate the local max and local min points using the graph. And then give intervals where it's increasing, decreasing, identify turning points, find the least possible degree. So you're just going to look at the graph and you are going to estimate. So right here, this is a local min. I'm going to say it's at -1/2, -5. It's just an estimate. We can vary on that. And then we have a turning point right here. I'm going to say that that's at 1,4. If you said 1,5, fine. I don't, that's okay. And then we have another turning point here. We can say it's at 3. You could say it's a little bit beyond 3, 3.2, but 3 is okay. And it's down 15. You got to watch your scale on the y-axis. So we estimate them. We're not going to all exactly agree on how we estimate them, but they should be in the ballpark. Now we're going to use those to answer the rest. So approximate local max and local mins. So we have local max. It is the y value. So the local max is right here. In that vicinity, it's a high point. And it's the y value. So the local max is 4 when x equals 1. That's the only local max. For the local min, you have 2 of them. You have 2 of them. In those vicinities, they're the lowest point. So the local min is -5 when x is -1/2. And a second one is -15, and that occurs when x is 3. Give intervals where the function is increasing, decreasing. Reviewing this from the beginning of the year. You use the x coordinates of the turning points, the local max and mins. You use the x coordinates. And you always drive the car from left to right. So you start on the leftmost part, you're decreasing. Then you change to increasing, decreasing, then increasing. So we're decreasing, increasing, decreasing, increasing. And new this year, 25-26, is we include the points for increasing, decreasing. And the textbook, I don't believe does, but you need to know to include them. So for decreasing, we have -infinity to -1/2, including that. And then we have from 1 to 3. For increasing, we have -1/2 to 1, union 3 to positive infinity. And on positive and negative infinity, they are never included. They're not actual numerical values. identify your turning points. Well, each of these ordered pairs are your turning points. It's the places where they change from increasing to decreasing and vice versa. So the turning points are ordered pairs. So -1/2, -5, 1, 4, and 3, -15. And find the least possible degree. You count up the turning points and add one. There are 1, 2, 3 turning points. And so the degree of the polynomial, you have n-1 turning points, at least, possible. I mean, not at least, but up to. And so the degree it has to be at least degree 4. So it's got to be at least one more than the number of turning points. Okay, and then we have even and odd functions. And an even function is when you fold it on the y-axis, it falls on top of itself. When you fold it on the y-axis, it falls on top of itself. It has symmetry with the y-axis. That is an even function. The definition is if you replace x with a negative x, you get out the original function. Nothing changes. And that's what you're going to do algebraically, and I'll model that for you. An odd function is when it has rotational symmetry with the origin. When you have rotational symmetry with the origin. See if I can get this to work for me. So if I rotate this, watching, 180 degrees. It falls on top of itself. It looks exactly the same. That is rotational symmetry with the origin. And that's an odd function. Now, algebraically, when you replace x with a negative x, you get out the opposite of what you started. Every sign is opposite. So what we're going to do here, and this is the work that you need to show that's written, that's what's referred to in the directions. Analytic, algebraic. What I'm showing you must be shown to get any credit to show whether something's even, odd, or neither. Just stating it's even, odd, or neither gets you no credit. So the test is you replace x with a negative x. You need parentheses with the negative x and the power on the outside. And then you simplify. Well, a negative cubed will be negative still, and then you get a positive 12x. Notice that we started with a positive x cubed, now it's negative. We started with a negative 12x, it is now positive. If you take out a negative, you have the opposite of what you started with. You started with x cubed minus 12x, all the signs have changed, you have the opposite of it. And when you have the opposite, every sign changes, that is an odd function. Therefore, this is odd. This is the algebraic work you need to show. Use your notes to help you see that. The nice thing about even and odd is you do the same thing. It's just the result that tells you if it's even, odd, or neither. And so in part B, we're going to replace x with a negative x. You need parentheses around the negative x with the power on the outside. If you don't have that, this is going to be wrong mathematically, most likely. And when you raise the negative to an even power, it's going to come out positive. And so when you get done evaluating that, you have exactly what you started with. So when I replaced x with a negative x, I got the function I started with. And when you get the function you started with, f of negative x is f of x, that is the definition of being even. So therefore, this is even. So on the last one, again, testing, we replace x with a negative x. You need the parentheses with the power on the outside. And a negative to an odd power will be negative. And from where you started and where you ended, the x to the fifth changed signs, but the positive 9 didn't. You got halvesies. This is neither. It has to be exactly the same or exactly the opposite. Most polynomial functions are not going to be even or odd. Most of them aren't. But we do need to be able to identify it. And that's the notes wrapped up.